Um, Good morning. We are going to learn our first technique for separation of the organic compounds. If the organic compound that we are trying to separate is liquid from its impurities, we can use distillation. Um, Distillation can be used also to separate mixture of two liquids if they have different boiling point. So it could be solid from liquid, or if the impurities are liquid, solid, or if the impurities are another liquid with a higher boiling point, then we can use distillation to separate and purify the compounds. Purification for the compound, for organic molecule, it's major step, because if the compound is not pure, you will not be able to do a structure analysis or identify your compound. Your compound must be a pure sample. So, can you tell me how distillation works? What does it happen in distillation? What is distillation process? You can type your response. What is involved in distillation? In distillation, first you are going to place your sample in a boiling flask. You are going to heating up the mixture. Yes, very good. You would heat up the mixture to vapor. You take the vapor into a condenser, and from the condenser, the water circulation of the condenser is going to allow. Very good. Your responses are great. You are going to use the condenser to cool down the vapor and then receive it at the other end of the condenser as a more pure sample. The condition for distillation, as I said, is that your impurity must have a very high boiling, much higher boiling point compared to the sample that you are recovering at the time. So there might be, we have two types of distillation that we are going to discuss in this experiment. One is simple distillation and the other one is fractional distillation. What's the condition for simple distillation? Best temperature difference in the mixture component of the mixture when you are using simple distillation. What should be the difference in the boiling point of the component of your mixture if you are using simple distillation? 80 degrees, yes. 80 degrees is ideal, because what that means is that while the first component or the compound with lower boiling point is vaporizing, showing in the diagram, and I will assemble it soon. While the first compound is boiling, the other compound stays in the liquid form. So the vapor that is produced initially at the lower temperature is going to be only or mostly the first compound, or the compound with the lower boiling point. Now, after the first compound is removed or has vaporized, then you will you will see that your mixture stopped boiling. You increase the temperature. When you increase the temperature, the second compound starts boiling, and then you are going to collect the vapor of the second compound. And with the second compound changing to vapor to liquid, you are going to recover the second compound, if that is the purpose of the experiment, or if the purpose of the experiment is just to purify the first compound when it's removed, then you are going to stop the distillation, because you know that the certain temperature, which corresponds to boiling point of your first compound, or the compound with the lower boiling point, is going to show on the thermometer, and that temperature, if it increases higher than the boiling point of the compound that is desired or you're trying to recover, then the impurities or other compounds starts boiling. So you want to make sure that you stop the distillation after the temperature is after the plateau of the temperature, or when at the constant temperature, which is the boiling point of the first compound, you are recovering the first compound. When the temperature goes and reaches the boiling point of the second compound, at that point the second compound is boiling. Okay, two types of distillation. One is simple distillation, the other one is fractional distillation. The purpose of the experiment today is comparing simple distillation with fractional distillation. You are going to assemble the distillation first. Your hardware should be out. I'm not going to, it's not the perfect and ideal situation right now. I may not have everything out on the table. I have to get the equipment for you to assemble it. But the hardware that you need, you see on the diagram on page 15 of the lab manual. You need a heating mantle. These heating mantles are not designed to be connected to the wall, so you should never connect them to the wall. They should be connected to a power regulator. So we have a power regulator that we are going to use and connect the heating mantle to the power regulator. I'm not going to connect the power regulator to the wall, or if I do connect, I'm not turning on. That would be the last step. First, we are going to work on the assembly of the distillation. You are going to use 100 milliliter flask based on the procedure for this experiment. And it's important to use a proper size, because the level of the liquid in the boiling flask cannot be too high, cannot be too low. Because if it's too low, then you have dead space here. A lot of vapor is going to be trapped there, and it doesn't make it to the condenser. So basically, your percent recovery is going to be lower, because it takes a lot of this space is taking some of the vapor, and it has to be filled up completely before it actually escapes the flask and it goes to the condenser. So the proper level is between 1/3 and 2/3. So the design of the experiment, it's going to show you, or the procedure would tell you what size of the flask you are using. When you take the flask, you also have to take a donut that, of course, is not edible. You are going to leave it inside the donut. You should never leave round objects on the surface, because they can roll, drop, and break. Your the clamps that you are using, utility clamp is used to hold the flask. So when you are assembling, you want to make sure you always use utility clamp for the flask, boiling flask. Use a 3-finger clamp to hold the condenser. The good thing about this 3-finger clamp is that the angle and the arm length is adjustable, so you can have better setup for your condenser. So if you have your hardware set and then you bring the glasses, the chance for lab breakage is lower. So let me find some glassware here to I wish we had.
I can move those over there.
It's recording. We try to get less distraction here. So it would be nice if we had at least one drawer or two of these things complete. That's all right. The setup sheet didn't have the grease.
The grease is there.
And then accept. Oh, perfect. Thank you. See it. Okay. So we are going to follow the glasswares from hot to cold. That means from the side that the heating mantle, we are going to start assembling the glasswares. First is the boiling flask. We are going to hold the boiling flask using or secure it using utility clamp. Then is the distillation head. This piece distillation head. Anytime you have glass joint, you must grease the glass joint and make sure that they are clamped. Okay. So you are going to use the glass joint. I am looking for the blue clamps or chem clamps, so they are also helpful to get the two glass joints together and it doesn't separate. It's very important because you want to make sure that you have a sealed system. If there is an opening or gap between the glass joints, the vapor, the first opening that vapor will find is going to escape from that. So we must secure it so we have a sealed system. You have a thermometer adapter. The thermometer adapter glass joint again. We are going to attach the thermometer adapter to the distillation head, and thermometer is going to be inserted into this rubber piece. To insert the thermometer, you would hold the thermometer and twist and push, like twisting, not force it. And when you are holding, you have to hold it low, so it would minimize the lab breakage. The height of the thermometer bulb should be just below the neck of the distillation head. If it's too high, it's not going to record the temperature of the vapor. If it's too low, then it would record higher temperature than the boiling point. A condenser. Condenser is going to be attached to the distillation head. Your distillation head or the glass joint again needs to be greased. And distillation head is attached to the condenser. And right away, you would use the blue clamp. It has like two rings, small and larger. And when you attach the two glass pieces together, I'm going to show you closer here. When you are attaching the glass pieces, see this area has a larger bump, like, and then smaller. So this cap clamp has to go just in between in a way that the large side would stay on the larger diameter and the small side on the other side. And you hold your thumb underneath, you push it from the top. If you try the opposite way, it's not gonna be easy to fit. And even if you force it, it's not going to hold. And you want to make sure that this cap clamp, it doesn't go only on one side, because if it goes only on one side, there is no benefit to that, because then still it's not going to hold it. The only way that it's going to hold is if you have it just at the joint and the large side in the large part, and then the smaller diameter in the smaller side. I need another of those, and I keep promising myself that I will come in and get equipment all in one place, but they are not too far. So we just connect this and use cap clamp. Okay. These clamps are not strong enough to hold the weight of the condenser. We want to make sure that the condenser is secured using this 3-finger clamp. Okay. We are going to use a graduate cylinder to collect. You see the height now is too low, so I cannot move one piece of the glass only to bring it up because everything is connected. So I have to make all the clamps loose. And when you are working in group, when we have 2 people here, it's easier. And then because each one, you can get help from your lab partner. If not, you use both hands and move it up, then secure it. It has to be aligned, not too much, not too high compared to the height of the graduate cylinder. So what is the problem? If it's too high, if it's up high here, the hot solution, or even though it condenses, it changes to liquid and it drops, but still is hot. And if you have too much of a gap here, because it's hot, some of it can, before reaching the graduate cylinder, it can vaporize actually. I have I keep iron ring, I have to explain this. I keep iron ring underneath this heating metal because I can adjust the height up and down. And whenever I'm done with the experiment, I can just drop the iron ring, drop the heating metal, rather than just turning off the heating at the power regulator. Because if I turn off that, this is still hot, and you cannot distill to dryness. So you have to make sure that it's when you stop distillation, the heat is actually removed. Okay, a simple distillation is already set up. Going to look for your questions. Do you have any questions? If you have any questions, please type your questions, and then I will get the sample into the flask, start distillation. The last part is it's connecting the condenser to water hose to have a gentle flow of water in the condenser. The water should be going in from the lower end and out from the upper end of the condenser. Okay, I'm going to detach the flask so I can get the chemicals in. And place a boiling chips in. 2-3 boiling chips. So what's the purpose of using boiling chips? To a smooth boiling, very good. So it would prevent bumping. And what is the purpose of greasing the glass joint? There are two purposes for that. I mentioned one, and I would like you to ask you for the other purpose. While I'm getting the chemicals, please write your response. How much of chemicals should I use? Do you know which chemicals you're using? Still very good. So we're using cyclohexane and toluene and 10 milliliters of each. We are going to mix it, and bring it right back. One was for sealing, that's the greasing, and what is the other reason? Okay. I reconnect the boiling flask and bring the heating mantle back up. And start the experiment. So to start the experiment for distillation, to collect sample, first we are going to turn on the water. And to turn on the water, you have to go very gentle turning on, because if it's too fast, with high pressure, it's going to cause like water splash. So we try this very gently, and the hoses that I'm using is not, sometimes they're old, but if you go very gently, it should work. Then you turn on the heat. You can turn on the heat, adjust the power regulator higher to begin with, like between 60 and 70 to begin with. As soon as you see your sample starts boiling, then you can lower it for gentle boiling. What happens if you heat it up too fast? Okay, your answer to first question you have that it water splashes. When we do distillation, we often have a trip to Splash Mountain, and it happened again, but it's okay. It's working now. The only thing I worry about is the water getting on electronics. So I keep the electronics on one side, water on the other side. I try to. Okay, your answer for the first question is that greasing. One purpose is to create like seals system, so the vapor does not escape from the openings. And after, like, you're done and you add your sample, you want to make sure that your setup is all put together properly. There is no gap, because sometimes by moving one piece, the other one is going to move. So you check it, you double check it before you turn on the heat, or before the sample starts boiling. And the other one, the other reason is that glass has low boiling point, low melting point. So if you don't grease these glass joints and you start heating with the high heat, these two pieces can freeze together. So it would be hard after you stop heating, then it would be hard to remove it. They kind of get stuck together and you won't be able to separate them. But when you grease it, it's going to be easy removal, and it separates well. Sometimes you have to break, if it starts, sometimes you have to break one piece in order to get the other one, or you can't separate them. So that is the other piece. Now, the second question, or the next question that I asked you was, what is the purpose of gentle heating? You cannot heat too high, too fast. There are a couple reasons for that also. So what I'm asking you now, these are good points that you could use for your discussions, because then now you know how to write the discussion. It's just the why and hows and control conditions. One of the reasons for not heating up fast is, like, if you have vigorous boiling, especially if the flask is more than half full, the liquid can bump into the condenser. So if the liquid does not change to vapor, then you can see that the liquid, which is a mixture of two, is going to be transferred to your graduate cylinder. The other problem is that if you generate too much vapor at once, your condenser doesn't have the ability to cool it down. The water flow is not, the temperature of the water is not too low, or any reason, because there is like capacity for this condenser, how much vapor it can be cooled down, and it depends on the specific heat and other theories. But in general, if you have too much vapor coming through the condenser and it doesn't get a chance to condense, change to liquid, then you would see vapor coming up to the end of the like the receiving, or this adapter, vacuum adapter that I have for collections. So we see vapor escaping, and that vapor escaping means what? Your sample, you're losing sample. So you're not going to be able to get the or recover the sample entirely. You're going to get partially, and you lose some of those samples. Two problems with that: low percent recovery. A second problem, you don't want to inhale the vapor of those the chemicals. So this is start boiling. The assembly of distillation is the major concern for this experiment. The other concern for the experiment is to collect the numbers. You are going to collect the temperature of the vapor, or the thermometer, for every milliliter of the sample that you are recovering. And you're starting with the first drop of the sample. So you have your tables in your lab notebook created with like the volume versus the temperature. And I'm going to help you collect these data first before I set up the fractional distillation, because it's a fast experiment. Otherwise, usually when I have a downtime, I can go ahead and set up the fractional distillation. But this simple distillation doesn't take too long for recovering of the sample. The sample is boiling now. I'm going to take the camera and show you. See that sample is boiling. If you want to take a picture of it, you can do like a, I don't know, we can use your cell phone to take a picture of the screen or do a screenshot. You can, then you could have that as like have to assemble based on the equipment that we have in this lab. So it is boiling now, but we are not recovering any liquid yet. We're just waiting for the first drop. The first drop came in. You see the first drop is dropping now. With that first drop, you need to record the temperature, and the temperature is 50 degrees Celsius. Okay, record the temperature 50 degrees for the first one. First drop. 50. And then I wait for the 1 milliliter. As soon as I collect 1 milliliter of the sample, then we need to record the temperature again. Yes, it's mixture of the two. Yes. Graphs or tables. You have to have a data table first. That's your chart data in order to plot the graph. So first you are going to collect the data, record it in a format. Then you would use the Excel program, probably in order to, or any other program to plot your graph. And when you plot the graph for simple distillation, and you plot the graph for the fractional distillation, you compare the two graphs, and with the comparison of the two graphs, you can compare the efficiency of the two methods. 1 milliliter, 55. At 1 milliliter would be 55 degrees Celsius. So record the number. For 1 milliliter, 55. For a perfect distillation, the temperature is going to increase. It would stay flat. Temperature is going to increase and stay flat. The first plateau or the flat part of the graph, this is the milliliter or the volume versus temperature graph. During this collection or this time, you are collecting your first compound. Then the temperature is going to increase for it to reach the boiling point for the second compound. And when the temperature reaches the boiling point of the second compound, so that's the boiling point, this would be the boiling point for your second compound. So boiling point for the first compound, boiling point for the second compound. This is a perfect graph under like perfect condition, but the lab condition is not the perfect condition, and I'm going to show you other graphs that you might see. Let me bring like different color. I can draw it on the same graph for you. Okay, we are still waiting for the 2 milliliter collection. So the graph that you get from your data today, it may not be straight like this. So you might get something like that. Still, you see you have a plateau, small plateau for the first compound and a plateau for the second compound, or mixture still and a plateau here for the second compound. So comparing the graphs that you have for both simple distillation and fractional distillation to this blue line or the blue curve for perfect distillation, the closer the shape of your graph is to the perfect graph, the more efficient or the better your distillation technique is. Ideally, which one is better, fractional or simple distillation? For separation purpose, it's going to the fractional distillation. And why fractional distillation is better? We have to explain that the process of fractional distillation, how does it discriminate or how it's going to be affected by the impurities is going to be left behind. Fractional distillation is a better technique. So if you keep the same mixture for fractional distillation, the fractional distillation curve, it should be closer or better match with this perfect separation of two straight lines at the boiling point of the first compound, boiling point of the second compound. And we are still waiting for the 2 milliliter, 2 more drops, it should be 2 milliliter. I lowered the heating rate, so I get better separation. The vapor is now it generates less vapor, so it takes more time. Okay, 2 milliliters, 55. 2 milliliters, 55 degree. Three milliliters actually increased to 60. 3 milliliters, it increased to 60. Or 60. It moved up again. So for 3 milliliters, record 65, please. 3 milliliters, 65. Your 4 milliliters. 4 milliliters, 66. 5 milliliters, 67. 6 milliliters, 67. 7 milliliter is 72. 8 milliliter also stay at 72. 72 for 8 milliliter. Do you see the setup now? The dripping of the and the volume being collected? Yes. Okay. Okay. 9 milliliters, 73. Okay. 10 milliliter is 74, and I'm switching the graduate cylinder because after the 10 milliliters is not graduated. 74 for 10 milliliter. Okay. 11 milliliter, 75. 12 is 75. It's not 13 yet, but the temperature stays kind of constant. It's not bad. 13 milliliters. Did I give you the 13? 76. And 14 milliliters is 77.
Yes.
It's slowing down because we are kind of running out of the. Okay. 1578. And with 15 milliliter, I think we should be fine. We can stop the experiment at this point because I'm going to see, actually, I'm going to watch if we can collect just 1 more milliliter. It's fine, but with the fractional distillation, we normally cannot go past the 14. It kind of dries up, or it could be that now we have a better sealed system because I've kind of made sure that it is sealed. But when we were working with the students, we never had this past 14, which is okay, which is good. But we should not aim for 20 milliliters because if you recover 20 milliliters, that means the flask is completely dry, and distillation should never go to dryness. 16 milliliter, 79. Okay, I'm going to stop the distillation. So I said, to stop the distillation, you need to first turn off the power regulator, unplug the power regulator, lower the heating mantle, because even though I turned off the power regulator and then I unplugged it, this is still boiling, see? Because the heating mantle still is hot. So if I want to stop the distillation, actually, I have to drop down the heating mantle. Lowering a level of ironing, I lower the heating metal. And I wait, and sometimes you can take it to the other end, like move it around so it's not heating indirectly. Even up to 16 milliliter, it's actually now dropping down because I dropped the heat. You collected 17 milliliter, but that value is not valid because I removed the heat. So 16 milliliter, that's where you stop. If I was going to deassemble this, take it apart, I would go from cold side. So I would take this piece out first, then the condenser. And in order to take the condenser out, I should close the water first and unplug the bottom from the, actually separate the hose from the faucet and allow the water to drain. I am going to use this condenser for the fractional distillation. So I'm kind of saving that for the fractional distillation, but I show you when I'm deassembling the fractional distillation to separate the water. You have to first unplug the hose from the faucet and let the water drain from lower end and then separate it. Because when it's full, you don't want to separate it while it's full. When we separate it, we keep it inside a donut again until we are done with the experiment and ready for cleanup. So we are done with this part of the experiment. So now I'll show you how to assemble the fractional distillation. The only difference between fractional distillation and simple distillation is addition of the fractionating column. How clearly you could see from there, don't know, but there is like a steel wool inside this condenser that they are kind of acting like fractionating column together with the condenser. The vapor, as it comes into the condenser here, is going to contact this steel wool as kind of an obstacle, so it doesn't go straight up, it's not open. The vapor, as it comes up, is going to lose heat. So this column is going to start getting warm and gradually is going to get warm. So now we have a mixture of A and B. A has lower boiling point and B has higher boiling point. So when we have this mixture coming up, the vapor of A and B at the beginning, both of them would condense and go back. But since as they condense, the fractionating column starts getting warm, vapor of A with the lower boiling point can survive longer than the compound with the higher boiling point. Because as soon as the temperature drops down from the boiling point, the vapor is going to go back to liquid. So we have two vapor, mixture of two vapor going up. Vapor A is going to survive to higher distance, higher level. Vapor of B, it goes back. So every time vapor of B is trying to come up, because the temperature for the condenser is going to reach first the boiling point of the vapor A. So it's hot enough for vapor of A to survive, but is not hot enough for vapor of B to survive. It's cold for vapor of B to survive. So vapor of B is going to condense back and it goes back into the flask. This theoretical plate is called like theoretical plate that is forming along the fractionating column. Every time it pushes the vapor of B down. What does that mean? It means the chance that you can get more pure sample for A is greater when you are using fractional distillation. So that's in terms of the theory, you have like fractionating column, which basically discriminates between the vapor A and vapor B. Vapor A for low boiling liquid is going to survive and go up easier, has less trouble because as the vapor is condensing, the fractionating column is going to reach the boiling point of vapor A first. So vapor A would survive and it goes into the condenser and it would be condensed back. B, it keeps going back. When all the vapor A is gone, then the compound with B is only left in the flask, theoretically, and B starts vaporizing. When B vaporizes, now is going to, because B has higher boiling point, the temperature of the condenser or the fractionating column is going to go higher because it releases, when a compound with higher boiling point, it condenses, is going to release more heat and is going to warm up this fractionating column to higher temperature until it reaches a temperature that vapor B is going to survive. So you didn't see any gap or drop in temperature for simple distillation. I did not see that based on the data that I collected today. But for fractionating column, there is a greater chance that when the compound A is gone or is collected, then the temperature drops because compound B has not reached to the thermometer to show that increase in temperature. So that's based on the theory, difference between simple distillation and fractional distillation. For simple distillation, there is nothing preventing B coming with A. Both of them can go at the same time. It depends only on the boiling point of the compound. If the boiling point is too far apart, then A would boil first and B stays in the liquid. But if the boiling points are close to one another, both A and B can vaporize. With distillation, there is nothing that can separate them or discriminate after they change to vapor. But with fractional distillation, this mixture of the vapor, it goes up, it can go back down, and the B will go back down, and A would survive first. In terms of the equipment, the only difference is that you're adding a fractionating column. It's going to increase the height for your setup. So we have to shift everything much higher to higher level so we can fit this underneath the distillation head and we have better setup. So this level of receiving is going to go higher. So we have to add another ring stand with a utility clamp to hold the graduate cylinder high. So let me go ahead and do this now. Assemble it. To hold condensers, we are using three finger clamp. Sorry, not the ring. 3-finger clamp. Hold the condenser. Push this back so you can see what I'm doing here. water hoses is needed for the fractionating column. This is just to assemble the height, because I like to have a complete assembly first before I worry about the chemicals. So I'm going to assemble this part first and then open it to get the chemicals, to add the chemicals. So this one has to go up high enough to fit the distillation. So I make sure my glasswares are secure. I added like extra glass here. I have to use a cap clamp to make it sealed again. One thing I forgot, to re-grease the glass joint here. I'm going to take it out, even though it was steel, it was greased already from the previous setup, but it's better to make sure that enough grease is applied and it will actually help both aspects of greasing. Don't make like everything too tight first, because it's glass and it can break if you make it too tight. To make it like finger tight loosely in order to just secure it. And when you level off everything, then you can go back, make sure that everything is tight and secure. Okay, this setup is done so far, except for the graduate cylinder, because I do not want, as I said earlier, I don't want my graduate cylinder to be all the way down here, and then this drops coming down all the way, and it can vaporize again, or I can lose the compound. So I'm using another utility clamp to hold the graduate cylinder up. Now, the fractional distillation setup is ready. The difference is that I added this fractionating column here. We are using heating mantle. We are using power regulator. The water hoses are connected. The lower end to the faucet, water coming in from lower end and going out to drain. So this part of the hose is loose, is just for the water flow to go out. Water should be on gently. We should have a gentle water flow here. The receiving graduate cylinder is a higher level because we had to bring it up to reach this. The flask, I'm going to open this flask, clean it, get the new chemicals in, add the boiling chips, and place back. So I'm not using this right the way it is. I'm going to clean it, add the chemicals that I need for fractional distillation, which is the same, because we want to compare the two methods. And then I will put it back and turn on the water first, turn on the heat. So let me get the chemicals. evaporate. Okay, we will connect the flask, apply vacuum grease to make sure of a perfect seal system, and the heat might be more for fractional distillation because the second sample may not evaporate or the vapor may not reach the condenser easily, so we may have to increase the temperature. That clamp, the cap clamp, is going to actually help, but we still have to use a utility clamp to secure it, to make sure that is secure. Okay, bring up the heating vessel, connect to the power, turn on the water gently, and turn on the heat, and wait. We gotta wait for like 5 minutes. If vapor doesn't reach to condenser, then we have to wrap this distillation head up to from this area with aluminum foil, kind of helping the process because of these fractionating column that is here is not going to let the vapor to go up easily. Sometimes we have to wrap it with aluminum foil, but I beat first, and if it does happen based on the boiling point of the compound, if it happens within the 5 minutes, I'm fine with it, and I would just continue without the aluminum foil. Okay, it's going to take a few minutes before we start getting any drops. And while we are waiting for that, I can answer your questions. The barometric pressure, we do have one in the other lab. I will go get ahead and read it and come back. I'll give it to you. Sure. Any questions? Why do you think the temperature is dropping between the two distillation? That was a question between on your pre-lab as well. The temperature is dropping. Is the solution getting cold for temperature to drop? But the temperature of the solution would still be high, right? Because we don't stop heating. We can bring that. The temperature, no, the vapor temperature, okay? The thermometer is recording the temperature of vapor. So why there is a drop of the temperature showing on the thermometer? Okay, the mixture starts boiling, but it would be a while before we can get any drop really down here. So we just be patient with this, we wait, and hope that we get the vapors. And I'm waiting for your response. Anything that you might think of, like the temperature of the thermometer is dropping. I think I mentioned during explanation for fractional distillation too. The vapor is not the vapor pressure that is decreasing, is a good point. It's not the vapor pressure that is decreasing. In fractional distillation, you are going to have vapor of the first compound reaching the condenser, actually passing through the thermometer to reach the condenser first, right? And then the compound 2 is going to start coming up. So at the beginning, it's just the compound 1 with the lower boiling point that is going up and reaching the thermometer. So for thermometer to show the temperature, the vapor must reach up here. When the first compound is recovered completely, the second compound is still working its way up, is not reached yet, has not reached to this ball. So the vapor is going to actually drop. Has not reached the thermometer yet. Yes, that is right. The vapor of the higher boiling point substance has not reached the thermometer yet, and that's why we get a drop in temperature. And why drop in temperature? Because there is no vapor of the lower boiling point temperature up here anymore, because that went to condenser and we recovered as liquid. So there is no vapor for a short time. For short period of time, we don't have any vapor around the thermometer, so the temperature is going to drop. So if you see a drop in temperature, don't panic. That's what's happening there. So the first drop, we actually got to too quickly here. First milliliter is 76. My higher temperature. Let me. First milliliter is 76. Second milliliter, it's faster than what I was expecting, really. So first milliliter was 76. This is not the first drop. I missed the first drop. Leave it blank. 2 milliliters is 77. 3 milliliter also 77. 4 milliliter 77. 577. 6 milliliter is 76. It's kind of slow down. But yes, it went from the 5 is 77, 6 is 76. 7 milliliter 76. Eight milliliter 74. Have you looked up the boiling point for toluene and cyclohexane? Do you know which one has higher boiling point, which one is the lower boiling point? So you actually are working for your low boiling point first is toluene or cyclohexane? It would be nice. I mean, I don't want you to post it up, the answer, but I want everyone to look for that for their own reports and discussions. So at least you can predict which one is coming, which compound is that. Not predict, to conclude which compound is coming out first. Is it toluene or cyclohexane? 9, it 70, actually dropped down to 70, and the vapor slowed down actually. So from now on, it looks like that we are either waiting for compound B or the last drops of compound A. This is very slow now. And I want to show you how this fractionated column actually is returning the compound B. See this distillation? For simple distillation, you don't see that return. You don't have that return going back to the flask. When vapor it vaporizes, it goes to distillation head and this directly to the condenser. But for fractional distillation, this actually compound B is the one that is being pushed back. It would be nice if you could take the screenshot. I actually hold it up for you to see the fractional distillation earlier. And if you didn't take a screenshot or picture based on this lab setup for the fractional distillation, I can hold it up again for you. Okay, 66 for 10 milliliter. To change the flask, change the eleven milliliters is 76. Okay, 12 milliliters, 84. 13 milliliters, 88. 14 is 92. Okay, when you are plotting the graph, make sure you plot the graph in two separate graphs, not on the same graph, and you are more concerned about the shape of the graph, not the actual like boiling point for the first compound or boiling point for the second compound. Because the setting on the thermometer kind of changed from the first distillation to the second distillation, and it could have record different temperatures or like higher temperature if the setting is lower. And I tried to go back to make it the same. It didn't happen. So what was the reason? But it was the same thermometer. We just have to look for the shape of the graph. The numbers are not exact the same. So 15 milliliters is 93. And 1694. I'm going to just collect one more to see like if we have like a stable number here. Looks like it. We reached a good plateau. It's not straight, but still. 17 is 94. Okay, going to stop the heat. Turn off heating mantle. I'm sorry, the power regulator. Unplug. Lower the ring to lower or remove the heating mantle. Put it on the side to cool down. And wait for all the vapor to go to condenser. Wait until the vapor inside the flask condenses back, because we don't want to open it right now, because if you open it then you're going to get the vapor coming to our face, and we don't want that. We're not going to take this graduate cylinder quickly because there might be a drop still coming, last droplets from the vapor that is remaining in the condenser. So we make sure that there is no drop coming out before we actually remove it. So wait, and like in 2 minutes, if there is no drop coming out, then I can stop the or deassemble the fractional distillation. You remove the hose from the lower, disconnect the hose from the faucet, from the lower end. The water drains out. Now the condenser is empty. There is no more drop coming out. We are going to start deassembling from the cold end to the hot. Because when we started, we went from the hot to cold. First we used the flask, then the fractionating column distillation head condenser. Now we have to deassemble it. We disconnect the power first, then water, then we take apart from the cold end to the hot end, one piece of glass at the time, and we can put it back where they belong. We don't want to have them on the bench top. So disconnect the hoses. get the Chem Club out. And take condenser out. Just one piece at the time. Put it in proper place, then go for the next one. So we're gonna have to wash this before putting back. To take the thermometer out, just twist and pull from the thermometer adapter. You twist it and pull to separate. This piece is still is hot. I'm just going to give a couple more minutes to cool it down before I take it apart. The disposal of the chemicals, they must go properly disposed. If we have a container in the fume hood that is labeled for distillation, we place it in that. If not, it would be non-halogenated organic waste. Okay, I'm going to stop the recording at this point because from now on is more of a data analysis. I'm not ending the lab, but I'm just going to stop the recording because we are done with the experiment. I'm not leaving yet. I'm just okay. The barometric pressure. Okay, good question. You just have
The barometer is in the
okay. You can record that number, and I'm going to stop the recording. Then we will work with your questions, and then you spend the rest of the lab time for the data analysis.